Okay, students. Good morning once again. So the next topic is your basic characteristics of the jump. Okay. Okay. So here, whatever we have derived two expression for your depth of flow before the jump and depth of flow after the jump. Okay. So you can write here y1 is the before the jump, y2 is after the jump, and fr1 is the Froude number before the jump, which is always greater than 1. So whenever we talk a hydraulic jump, if we draw a specific energy curve, this is our specific energy here, and this is your depth of flow in y-axis. Okay. So for a particular distance, this will be the curve, and if you join with the critical flow, it divide into two parts. One is your supercritical, one is your subcritical. Okay. So in a hydraulic jump, when your flow jumps from supercritical, to subcritical, then only we can say it's a hydraulic jump. So your first depth of flow, that is before the jump, it is in supercritical. Okay. And so y1 is in supercritical and y2 is in subcritical. So we all know in supercritical your fr1 Froude number is always greater than 1. Okay. And in subcritical our fr2 is always less than 1. So that is why for your y1 value, whatever the fr1 is always greater than 1, and your fr2, that is Froude number after the jump, is always less than 1. Okay. So hydraulic jump occurs when the flow changes from supercritical to subcritical flow. So you write down this expression. Okay. Okay, so we move on to the next topic. Okay, that is basic characteristics of the jump, or you can say loss of energy in the jump. So here, loss of energy, that is when the jumps or the flow changes from supercritical to subcritical, how much loss in specific energy occur. Okay, that we are going to find out here. That E1 minus E2, E1 minus E2. E1 is the specific energy before the jump, that is in supercritical. Okay, and E2 is a specific energy after the jump, that is in supercritical. So del E is nothing but E1 minus E2. So here del E is equal to, we know in specific energy, if you remember, we will be having two components, that is one is depth of flow and another one is V square by twice G. Okay. So here for E1, that is your in supercritical, your depth of flow is Y1. So here in place of Y, we have considered Y1 plus V1 square by twice G. Okay. Minus for E2, again Y2 plus V2 square by twice G. Okay. So if you remove this bracket, then it will be minus, and this plus is there, again it will be minus. Okay. And in place of V, we can write Q by A, this serves by area, and in place of area you can write this serves by B into Y. Okay, for rectangular channel, if we consider the channel is rectangular. Okay, so this is in place of velocity, you can write Q by B into Y. So here also we have replaced that velocity V square by Q square divided by B into Y whole square. Okay, similarly for second condition also, for V2 also. Okay, then we all know small q is nothing but discharge per unit width, Q by B. Okay, so Q square, small q square is equal to capital Q square divided by B square, that is the width of the channel. Okay, so here you can directly write small q value, and twice G is already there. Here this is, we can take common, so 1 by y2 square minus 1 by, sorry, 1 by y1 square minus 1 by y2 square. Okay, this is your simple mathematics. Y1 is already there, here is minus y2, so it will be minus y2. Okay, then in this two term, your q square by twice g b square is common, but q square by b square we have considered small q square. So small q square by twice g is common in this two term. Okay, and the left out is 1 by y1 square, here we have minus, so it will be minus 1 by y2 square. Okay, so after that this will be y1 minus y2 q square by twice g. Then if you can take LCM. Okay, so it will be y2 square minus y1 square divided by y1 square y2 square. Here again a square minus b square, you can write a plus b, a minus b. So till here you first write. After this, now we have to go back to this derivation or rectangular channel. You have this expression. We are going to use this expression, you see, here, this expression, okay? Twice q square by g is equal to y1, y2 plus y1. We use this expression here, okay? We use this expression. This expression we have derived already in last class, in previous class, okay? So this derivation we directly use here and see here, okay? So you can write here, we have q square by g here. Here is twice q square by g. So you bring the twice in the other side, okay? So that is why we have taken common y1 y2, so it will be y2 plus y1 divided by 2. This 2 will be there, this 2. Okay, now we are substituting this equation here in this equation. Okay? Substituting this equation here in this equation. Okay, here del e is equal to y1 minus y2 plus will be this equation. In place of here q square by g, we are going to substitute this equation, y1 y2 y2 plus y1 divided by 2. Okay, multiplied by half is already there, then y2 plus y1, y2 minus y1, y1 square y2 square. Okay, other all the terms will remain same. Okay, okay, then if you do further simplification, after that it's very simple. Okay, just you have to simplify and you have to bring an expression for del e, okay, in terms of y1 and y2, because all the terms are y1 and y2 only. Okay, only you have to do the simplification, that's it. How you simplify, it's up to you. Okay, you can use any simplification, okay, process. It's up to you. You first plus or then multiply, or first multiply then plus you add. It's up to you, it's completely up to you. Okay, if you do the simplification you will get this expression. Okay, so you can directly write down this expression. Okay, and you, this simplification you try to do at home. Okay, after this you only do the simplification fc, you are getting the same expression or not. Okay, if you find any difficulties then we will discuss again. Okay, no issue. Okay, but I think you can do, because it's just a simply simplification you have to do. Okay, don't have to substitute, you don't have to take reference of other also, you just doing the simplification of your own. Okay, how you feel like to do. Okay, and see is automatically we will get this expression. Okay, so you can write the above equation is the loss of energy in hydraulic jump in rectangular channel. Okay, whatever we have derived, this is only for rectangular channel. Okay, so we have another few topics to discuss. One is your this relative loss of energy. Then we have efficiency of the jump. Then we have height of the jump. Okay. Then we have types of jump. Okay. Okay. So after that we have length of the jump, and then we can solve few numericals related to the jump. Okay. Then after that we can complete our syllabus. Okay. So very few things are left out. Okay. So we continue in the next class. Okay. That one is your relative loss and one is your efficiency of the jump. Okay. We'll continue in the Thursday.